Greetings to everyone, my name is Daniel Ochoa, and today I'll be presenting the work titled Robust Optimization over Networks Using Distributed Restarting of Accelerated Dynamics, which is a joint work with Professor Jorge Poveda, Cesar Uribe, and Nicanor Quijano, and will be published next year in the IEEE Control Systems Letters. So in this work, we were motivated by the ubiquity of multi-agent systems in the modern world, whose presence spans from power and water distribution systems to mass transportation and network control. And we focused our work in the study of optimization algorithms over networks, over these kind of networks. Since the large scale of a lot of these systems impedes a centralized computation of optimal solutions, either because of time or money constraints, we center our attention in the distributed solution of such optimization problems. With this in mind, we model the multi-agent system as a graph, where each one of the nodes has a local cost function that depends on the whole state of the network, and focus on minimizing the sum of the local functions over all the nodes. Since our aim is to solve the problem in a distributed fashion, where computation can be carried through only by using local information, we instead treat the equivalent problem where there is a local version of the whole, local versions of the whole network state kept separately in each one of the nodes, and where we enforce this constraint, where this L is equal to the Kronecker product between the graph of the Laplacian matrix of the graph and an identity matrix of suitable dimensions, and it's called the communication matrix of the graph, and where if we post this in a fully connected graph, it's actually equivalent to having each one of these ZIs equal to each other whenever we're treating feasible solutions. And hence, if we solve this optimization problem, we're actually finding an equivalent solution to the optimization problem exposed in a previous slide. It's actually known as the consensus optimization problem in the literature. So aiming to solve this, we wanted to have three main properties. First, we wanted to have fast rates of convergence. We wanted to do so while still being fully distributed and having robust margins against in the presence of arbitrarily small disturbances that can be adversarial in nature if someone is attacking the network, or arise from numerical approximation errors during the computation, which is a practical assumption that can happen every time we're trying to find an optimal solution in a computer. In order to achieve these fast rates of convergence, we look into implementing the renowned Nesterov accelerated gradient method. But if we implement them as they are with any other kind of modification in each one of the nodes, this actually poses a problem because, as has been studied in the literature, although this guarantees convergence of the solutions of the dynamics into the set of minimizers of a set of a class of cost functions, it actually has robustness issues when small disturbances are introduced to the system. This is actually a simulation of the system above for a given cost function, and we actually can make the system unstable if we introduce these arbitrarily small disturbances. Recent works have shown that robustness properties on these dynamics can be obtained by endowing them with discrete time restarting mechanisms that persistently reset the momentum and timer states. They reset this, in this case, the Y and the T, in order to achieve this robustness property. So our goal will be to implement this, but we want to do so in a fully distributed manner. In order to do this, we face the problem that we have to go from just one timer to having a different copy or a different timer in each one of the different nodes. And though we'll need to implement a mechanism that actually synchronizes all the different clocks of the network in order to achieve the accelerated the accelerated rates of convergence. Additionally, in order to keep the possibility of having distributed updates of the states, it's important that we maintain the sparsity of the communication matrix. So, although solutions to each one of these problems have been found individually in the literature, to the knowledge of the authors, it remained an open question whether or not it was possible to reconcile these three properties under the umbrella of the consensus optimization problem. As we show in our paper, the answer to this question turns out to be actually positive. We can reconcile all of them, and with this, our main contribution was the formulation of the hybrid accelerated restarting distributed dynamics, or HARD for short, which are the first robust and distributed restarting based accelerated dynamics for the solution of the network consensus optimization problem. So now the question is, how do we do this? So we make use of two main tools. The first one is the hybridynamical systems formalism, which allows us to study in a rigorous way how the periodic restarting of the momentum and time variables actually endows the system within a well-posed hybridynamical system, which in conjunction to being uniform globally asymptotically stable, which is equivalent to having the existence of this scale function, implies robustness properties under arbitrarily small disturbances, which is one of the properties that we want for our algorithms. So that's why we used hybridynamical systems. And on the other hand, instead of treating the problem in the primal domain, we go to the dual domain, right? Where the problem becomes an unconstrained one, and where the gradient of the cost function is closely related with the communication matrix. So this is important to note for a further slide. Explain. So these are all tools. In addition to these tools, we impose three main assumptions. First, we suppose that the local cost functions of each one of the nodes are continuous and strongly convex. Second, we suppose that the communication graph is undirected, connected, and time invariant. And finally, we suppose that the level sets of the dual function, cost function, with domain restricted to the kernel, to the orthogonal complement of the kernel of the communication matrix are bounded. This is actually important. This last one is important because we make use of the hybrid reduction principle in order to provide certificates of robustness and stability for the hard dynamics. Yeah, that's one of the assumptions that the hybrid reduction principle needs, is that the set of points to which we are trying to converge is bounded. The other first two are really common in the literature, so shouldn't be worried about that. So yeah, these are our dynamics: the hybrid accelerated, restarting, distributed dynamics, hard dynamics. We have flows and we have jumps because it's a hybrid dynamical system. In the flows, we have the dual variable of the optimization problem. We have the momentum, and we have all these different bunch of timers, as I said before. And this is actually the flow map of the dynamics. It's closely related to the nested of dynamics, but instead of having the timer times this gradient, we actually changed the order and put this matrix inside of the gradient. And this is done as this in order to keep the sparsity of the communication matrix while still having all of these different timers that will allow us to have fast convergence rate when we achieve actually synchronization between each other. And we allow these flows to happen whenever all of these different timers are between the bounds tr and tr plus delta t. So this is are like a constraint that says when are the flows allowed. In terms of the jumps, we actually implemented this rule, which in a nutshell, it's allowing us to have that whenever a timer reaches the upper bound allowed for it, it resets itself, and it also resets the timers of all of the different adjacent nodes that are connected to it. Because this is we are supposing that we have a fully connected graph and undirected. This actually means that after the first reset, we have full synchronization of all of the different timers, and after that, we can have acceleration of the acceleration in order to achieve the fast rates of convergence. Additionally, we have this Q variable, which is important for a later reason that I'll explain, and which allows us to reset the primal variable either to itself or to the momentum variable. Okay, so our main theorem is this: under different and suitable conditions of the tunable parameters of the dynamics, the set of minimizers of the cost function is uniform globally asymptotically stable. Which, because we have a well-posed dynamic hybrid dynamical system, this implies robustness properties for the dynamics. Additionally, for each compact set of initial conditions, if Q equals 1, which is chosen whenever the primal cost function is globally ellipses, we can achieve linear rates of convergence. If Q equals 0, we achieve sublinear rates of convergence, but we actually have acceleration in the dual domain whenever the flows are allowed. Comparing this with a state-of-the-art algorithm, we actually find that we outperform that algorithm whenever we start synchronized. When we are not synchronized with the hard algorithm, after synchronization, the acceleration is achieved, and we can minimize the suboptimality measure. And it's important to note that both synchronization of the timers and restarting itself are important. The synchronization, if there is no coordination, we actually found that if the timers are all up by themselves and try to reset themselves without being coordinated, we cannot actually reduce the suboptimality measure. And if we don't restart the hard algorithm, we don't restart the timers, we have the robustness issues. So we always need to restart it in order to have these robustness margins against arbitrary small disturbances. So our conclusions is we propose the first algorithm that has distributed restarting of accelerated dynamics, where each node implements its own momentum and clock to coordinate its own dynamics, and where suitable robustness properties as well as linear convergence rates for strongly convex functions are achieved.